The concentration or strength of an acid, base, or other solution can be recorded by one of three chemical measures of concentration: molarity, molality, or normality. Each of these measures of concentration is defined by its own equation. Molarity is defined in terms of moles of solute divided by liters of solution. Molarity has units of moles per liter. The notation symbol for molarity is usually a capital M. The defining equation for molarity is shown. Molarity equals moles of solute divided by liters of solution with units moles per liter. Molality is defined in terms of moles of solute divided by kilogram mass of solvent. Molality has units of moles per kilogram. The notation symbol for molality is usually a small m. The defining equation for molality is shown. Molality equals moles of solute divided by moles of solvent with units moles per kilogram. Normality can be defined in two ways that end up as the same answer. First, normality is the equivalence of solute divided by liters of solution. Or, in its second form, normality is defined in terms of mass of solute divided by equivalent weight of solute times the liters of solution. Normality has units of equivalents per liter. The notation symbol for normality is usually a capital N. The defining equation for normality is shown. Normality equals equivalence of solute divided by liters of solution, or mass of solute divided by equivalent weight of solute times liters of solution. All give units of equivalents per liter. Normality might be more simply defined by the molarity of the solution multiplied by the valency of the solute. Valency is just the number of ions, protons, or electrons a molecule of solute gives up to the solution. Valency has units of equivalents per mole. The equation of normality in terms of molarity is shown. Normality equals molarity times valency. For better understanding, I give some examples of how each of these concentration measures might be calculated from given information. Example 1. Find the molarity and normality of 2 moles of H2SO4 dissolved in water to form 1 liter of sulfuric acid solution. Since we are given the 2 moles of H2SO4 solute and the solution volume of 1 liter, we can plug these values directly into the molarity equation. 2 moles of H2SO4 divided by 1 liter of solution equals 2 moles per liter of H2SO4, or 2m H2SO4. So, we have a sulfuric acid solution with a molarity of 2. The notation 2m H2SO4 can be read as 2 molar H2SO4, or 2 molar sulfuric acid. This molarity can be used to calculate the normality of the sulfuric acid solution. The normality equation requires the valency or the equivalence factor of the solute. The equivalence factor is just 1 divided by the valency. The valency N of a solute is just the number of ions, protons, or electrons that the solute will donate to the solution. H2SO4 will donate 2H plus protons per molecule, or give a valency of 2 equivalents per mole. The equivalence factor, 1 over the valency, is 1/2 moles per equivalent. We can plug the known molarity and valency values for the sulfuric acid solution straight into the normality equation. Normality equals M times N equals 2 moles of H2SO4 per liter times 2 equivalents per mole of H2SO4 equals 4 equivalents per liter of H2SO4, or 4N H2SO4. So we have a sulfuric acid solution with a normality of 4. The notation 4N H2SO4 can be read as 4 normality H2SO4, or 4 normal sulfuric acid. Example 2. Find the molality of hydrochloric acid solution consisting of 2 moles of HCl dissolved in 1 liter of water. First, we need to know that at 25 degrees Celsius, 1 liter of water has a mass of 1 kilogram. Since we are given 2 moles of HCl solute, we can simply plug in the known values into the molality equation. Molality equals moles of solute divided by moles of solvent equals 2 moles of HCl divided by 1 kilogram of water equals 2 moles per kilogram HCl, or 2m HCl. So, we have hydrochloric acid solution with a molality of 2. The notation 2m HCl can be read as 2 molal HCl, or 2 molal hydrochloric acid. We must be careful to distinguish molarity from molality. Remember, molarity is moles per liter of solution and molality is moles per kilogram of solvent. For example 3, let's go back to example 1 and calculate the normality of 2 moles of H2SO4 solute dissolved in 1 liter of aqueous solution from the equivalence factor and the equivalent weight of the H2SO4 solute. So we know we have 2 moles of H2SO4 solute dissolved in 1 liter of aqueous solution. A quick look at the normality equation tells us that we need to calculate the mass of the H2SO4 solute and we need to calculate the equivalent weight EW of the H2SO4 solute. Normality is the mass of solute divided by the equivalent weight of the solute times the liters of solution with units and equivalents per liter. Well, the mass of the solute is the 2 moles multiplied by the molecular mass of the H2SO4. The atomic mass of each component of H2SO4 can be found in most periodic tables. The atomic mass of hydrogen H is 1.008 grams per mole. The atomic mass of sulfur S is 32.06 grams per mole. The atomic mass of oxygen O is 16.00 grams per mole. So the molecular mass of H2SO4 is 2 times 1.008 plus 1 times 32.06 plus 4 times 16.00 equals 98.076 grams per mole. Since we have 2 moles of H2SO4 solute, the mass of the solute is 2 times 98.076 grams per mole equals 1.96.152 grams. The equivalent weight of an acid solute is the mass of solute that will neutralize 1 mole of hydroxide ions into water, H2O. So we need 1 mole of H plus protons to bond with 1 mole of OH negative ions to form neutral H2O. Since we know that sulfuric acid has 2 H plus protons available for dissociation from its conjugate base, SO4 negative 2, or a valency of 2 equivalents per mole. Its equivalence factor F is 1 over the valency equals 1/2 moles per equivalent of H2SO4. So we can calculate the equivalent weight EW of H2SO4 acid solute that will neutralize 1 mole of hydroxide ions. Equivalent weight equals F times molecular weight of H2SO4 equals 1/2 moles per equivalent times 98.076 grams per mole equals 49.038 grams per equivalent. We could have got the same value by dividing the molecular weight by the valency, 2 equivalents per mole. We can plug the mass of H2SO4 and the equivalent weight of H2SO4 solute back into the normality equation. The normality equals the mass of the solute divided by the equivalent weight of the solute times the liter of solution equals 196.152 grams divided by 49.038 grams per equivalent times 1 liter equals 4 equivalents per liter. So we have 4N-H2SO4 or 4 normal sulfuric acid solution just as we found in example 1. In example 1, we calculated the normality from the molarity times the valency. I agree it's easier to calculate the normality from the molarity, but at least we know how to calculate the equivalent weight of the acid if we ever run across a problem that ever requires us to calculate the equivalent weight of the acid. So far in these examples, we have been given all we need to calculate the molarity, molality, and normality, just as in a high school chemistry book. Let's try a more difficult problem. Example 4. What is the molarity, molality, and normality of the combined solution when 2 moles of HCl gas is bubbled into 1 liter of water at 20 degrees Celsius? Assume all the HCl bubbles are dissolved in the water. Since the amount of HCl solute and water solvent are given, the molality will be easiest to calculate, so we get the molality out of the way first. The molality equation is moles of solute divided by mass of solvent, with units in moles per kilogram. We have 2 moles of HCl solute. 1 liter of water at 20 degrees Celsius has a mass of 1 kilogram, so we plug these values into the molality equation. Molality equals moles of solute divided by mass of solvent equals 2 moles of HCl divided by 1 kilogram of H2O equals 2 moles per kilogram of HCl, or 2 molality HCl. So we get the molality of 2 or 2 molal hydrochloric acid. To get the molarity, we need the liter volume of solution, which will be slightly greater than the original 1 liter of water. If we had an actual experiment in front of us, we might have a graduated cylinder that we could use to measure the volume of hydrochloric acid solution. Since we are doing all this by math methods, we need a table of HCl solution characteristics that includes the density versus different concentrations of HCl aqueous solution. The Wikipedia page on hydrochloric acid just happens to provide such a useful table. We might make a first guess at the HCl solution molarity simply by using the 2 moles of HCl as the moles of solute and the 1 liter of water as the volume of solution. The 1 liter of water is not the volume of solution. This result will be an error, but the result will give us a good estimate of how large the error is when we arrive at a final approximation. We plug the first guess values into the molarity equation. Molarity equals moles of solute divided by liters of solution equals 2 moles of HCl divided by 1 liter of water equals 2 moles per liter of HCl, or 2m HCl. We know this 2 molar HCl answer is wrong, but it'll be probably close to our final approximation, as the volume of HCl solution will be only slightly greater than the original 1 liter of water solvent. We need to find the error. Looking back at the table, we note the mass fraction is in column 1, the density is in column 4, and the molarity is in column 5. From these table values, we can plot the molarity versus mass fraction, or molarity versus density, as I have done in the figures. We can see that in both plots, the curves are fairly linear. The curves are not perfectly straight lines, but they are straight enough that we could use a linear interpolation to get a good approximations for unknown values between the known values on the table. We can calculate the mass fraction from the moles of solute and volume of water given in the original question. The mass of HCl solute is just the 2 moles given multiplied by the molecular mass of HCl. The atomic mass of hydrogen H is 1.008 grams per mole. The atomic mass of chlorine Cl is 35.45 grams per mole. So the molecular mass of HCl is 1 times 1.008 plus 1 times 35.45 equals 36.46 grams per mole. Since we have 2 moles of HCl solute, the mass of solute is 2 moles times 36.46 grams per mole equals 72.916 grams. We already know the mass of 1 liter of water solvent is 1,000 grams. The mass of solution is 72.916 grams plus 1,000 grams equals 1,072.916 grams. The mass fraction is the mass of solute divided by the mass of solution. 72.916 grams divided by 1,072.916 grams equals 0.067961. So the mass fraction of HCl solution is 0.067961, or 6.7961%. Looking back at the table, we find that 6.8% is about midway between 0 and 10% mass fraction. To get a linear interpolation of the molarity between these 2 points, we must find the equation of the straight line between 0 and 10 on the molarity versus mass fraction plot. A straight line has the equation y equals slope times x plus the intercept. To get the slope, we use the slope equation. Slope equals dy dx equals y2 minus y1 divided by x2 minus x1. In this case, x is the mass fraction and y is the molarity. From the table in the plot, x2 equals 10 and x1 equals 0 mass fraction. The molarity y's are y2 equals 2.87 and y1 equals 0. So the slope is dy dx equals d molarity d mass fraction equals y2 minus y1 divided by x2 minus x1 equals 2.87 minus 0 divided by 10 minus 0 equals 0.287 molarity per mass fraction. Next, we get the y-intercept with a mass fraction x equals 0. We already know this intercept should be 0 molarity, but for the sake of the example, we can plug these numbers into the intercept equation. The intercept equals y minus slope times x. Or since we know that x2 equals 10% and y2 equals 2.87 molarity, The intercept equals 2.87 molarity minus 0.287 molarity per mass fraction times 10 mass fraction equals 0 molarity. We now have the equation for the line. Y equals slope times x plus intercept equals 0.287 molarity per mass fraction times x plus 0 molarity. Since we know the mass fraction of the HCl solution is 6.7961%, we can plug this value in as x in our interpolation line. Y equals 0.287 m per mass fraction times 6.7961 mass fraction plus 0 m equals 1.950469 m HCl. And we find the approximate molarity of our HCl solution is 1.950469 m. This is fairly close to our original guess of 2 molar. Remember, our original guess used only the 1 liter of water for the solution volume. This guess is wrong by an error of 0.05 molar or 0.05 moles per liter. Now that we have a good approximation for the molarity, calculating the normality of the HCl solution is trivial. HCl has only 1 proton H+ per molecule, so its valency N is 1 equivalent per mole. The normality is calculated from the molarity times valency. N equals m times N equals 1.95 moles of HCl per liter times 1 equivalent per mole equals 1.950469 equivalents per liter HCl, or 1.95 normality HCl. So we have hydrochloric acid solution with a normality of 1.95 equivalents per liter for 1.95 molarity HCl solution. We could also find the volume of solution by 2 methods. First, convert the molarity straight to the volume of solution. Or second, by looking at the table to get a density interpolation line, then by using the approximated interpolation density to get the volume of the solution. We can check both ways to see how much error exists. Remember, the table data is only accurate to 3 significant figures or 2 decimal places, so we cannot expect the accuracy to be great. To get the volume of solution straight from the molarity formula, molarity equals mole solute per liter solution. We rearrange the formula to get the volume of the solution and plug in the known values. Liter solution equals mole solute per molarity equals 2 moles of HCl divided by 1.950469 moles per liter HCl equals 1.0254 liters HCl solution. So the volume of solution is 1.0254 liters. To get the volume of the solution by interpolating the density. We know from the table that the density of 2.87 molarity HCl is 1.048 kilograms per liter. This will be X2 equals 1048 grams per liter, and Y2 equals 2.87 molarity. We can use these X and Y values to find the slope of the interpolation line. We should know the density of pure water at 20 degrees Celsius is 1 kilogram per liter, and pure water has a molarity of 0. So X1 equals 1,000 grams per liter, and Y1 equals 0 molarity. Plugging these values in to get the slope. Slope equals dy dx equals Y2 minus Y1 divided by X2 minus X1 equals 2.87 minus 0 moles per liter divided by 1048 minus 1000 grams per liter equals 0.059792 moles per gram. So the slope is 0.059792 moles per gram. Next, we need the intercept molarity Y, where x equals 0 grams per liter density. Intercept equals Y minus slope times x. Or since we know x2 equals 1048 grams and y2 equals 2.87 moles per liter, the intercept equals 2.87 molarity minus 0.059792 moles per gram times 1048 grams per liter equals negative 59.7917 molarity. So, if we use the interpolated slope of 0.059792 moles per gram and the intercept of negative 59.7917 moles per liter, along with a Y molarity of 1.950469 moles per liter, we get a density of 1032.6227 grams per liter. If Y equals the slope times X plus intercept, density equals X equals Y minus intercept divided by slope equals 1.950469 minus negative 59.7917 moles per liter divided by 0.059792 moles per gram equals 1032.6227 grams per liter. To get the volume of the solution, we divide the mass of the HCl solution of 1072.916 grams by the interpolated density. The liters of solution is 1072.916 grams divided by 1032.6227 grams per liter equals 1.039 liters. This is somewhat different from the 1.0254 liters of HCl solution we found from the conversion directly from the interpolated molarity. And this small error should warn us of the errors that can be accumulated from interpolation and from using rounded up experimental data. We can learn more from the hydrochloric acid properties table. The highest mass fraction listed on the table is 38%. The highest molarity listed on the table is a molarity of 12.39 moles per liter. A molarity of 12 is huge. At these high mass fractions in molarity, HCl solution is called fuming hydrochloric acid because at these high values, HCl is at or near its maximum solubility in water at 20 Celsius. At mass fractions much above 38% of the solution, the hydrogen chloride gas is bubbling out of the solution. As a last example, we might find the molarity of an acid dissolved in alcohol. At 20 degrees Celsius, the solubility of hydrogen chloride gas in methanol, CH3OH, is as high as 470 grams per liter. This solubility is about a third lower than the solubility of HCl in water of 720 grams per liter at 20 degrees Celsius. Example 5. What is the molarity of 3 moles of HCl dissolved in 1 liter of methyl alcohol solution? We bring back the molarity equation and apply it just as we did for the water solutions. Molarity equals moles of solute divided by liters of solution equals 3 moles of HCl divided by 1 liter of CH3OH equals 3 moles per liter HCl in CH3OH or 3 molar HCl in methanol. In the lab, we should be careful to mark that 3 HCl MEOH solution is dissolved in methanol. This marking is a safety precaution to ensure that no one in the lab mistakes the HCl methanol solution for an aqueous solution dissolved in water. Since the valency of HCl is 1 equivalent per mole, the normality of 3 molar HCl methanol solution is 3 normal HCl methanol. We need to weigh the mass of the HCl solution to back out the mass of the methyl alcohol solvent from which we could derive the molality of the HCl methanol solution. And that concludes my discussion of molarity, molality, and normality of acids and bases. Thank you for watching. If you enjoyed this video and want to help me make similar content, please like and subscribe.